So x. Now I multiply. X times 3x is 3x squared. X times 1 is 1x. Well, after you multiply, just like with any other long division, you subtract, okay? And when you subtract, really keep in mind that you're subtracting all of this. So I've got a 3x squared minus 3x squared, and I've got a negative 14 minus 1. So that gives me a negative 15x, and then we bring down, okay? Well, here we go. I'm now looking at 3x and negative 15x. Well, minus 5. Negative 5 times 3x is negative 15x. Negative 5 times 1 is negative 5. I'm subtracting something from itself. My remainder is 0. Okay? There we have it. And we could check it, right? If I wanted to check, that's that division algorithm. Division algorithm. I take my divisor times my quotient plus my remainder, and I verify that that's 3x squared minus 14x minus 5. And guess what? It is. All right. This one, a little more complicated. X squared minus 3x plus 1. And then 5x cubed plus 2x squared minus x plus 1. And again, I'm not worried about the negative 3x or the plus 1. I'm really just looking at my leading term. So x squared times what is 5x cubed? Well, times 5x. Again, I'm going to line up the correct degree terms and then multiply. So I have 5x times x squared is 5x cubed minus 15x squared minus 5x. 2 minus negative 15, 17, x squared, negative x minus negative 5x will be plus 4x, and then we bring down, okay? And so now I've got a 17x squared and an x squared. So I'm going to multiply by 17, so plus 17. And then 17 times negative 3, negative 51x. And then plus 17. And we subtract. 4x minus negative 51x is going to be 55x. And 1 minus 17, negative 16. And so here's how we write the remainder, 55x minus 16 over x squared minus 3x plus 1. There we have it. Okay, and let's do one more here. You might notice that we've got something missing, okay? Got something missing, namely, there's no x term, but we have to account for it. So the way we do that is to assign it a coefficient of 0. Okay. If I were missing x squared, I'd have a 0x squared. All right. If I didn't have the constant, I'd say plus 0. Okay. So here we go. Again, looking at the first terms, the leading terms. So x times what is x cubed? Well, x squared. Lining up my terms. So I have x cubed minus 5x squared. I am subtracting. So -4 minus -5 is 1. Then I bring down my 0x. Now I'm looking at x and x squared. So times x. X squared minus 5x. I subtract. 0 minus -5 is 5. And bring down. And then x times what is 5x? Well, 5. So we have 5x minus 25. 1 minus -25 is 26. We have it. All right. Okay, well, what about synthetic division? Synthetic division is pretty useful because it allows us to just look at the coefficients, okay? So here's what we're going to do. I'm going to take x minus 5, and what I'm going to do is this. I'm going to put that 5 right here, and then I'm going to bring these coefficients over here, okay? Leave some space and do this, all right? So it's pretty straightforward. What I'm going to do is I'm going to start by bringing this coefficient 3 down. And then all I do is I multiply and add. So 5 times 3 is 15. -14 plus 15 is 1. Then I do it again. 5 times 1 is 5. -5 plus 5 is 0. Now keep in mind what this means in terms of the degrees, right? I'm dividing, whoops, zooming in. I'm dividing square degree 2 by degree 1. So what this tells me here is this 3 is the coefficient of x, and 1 is constant. And so what does this equal? Oh, 3x plus 1. Of course, we could check it. Check all these. 3x plus 1 times x minus 5. Well, 3x squared plus x minus 15x minus 5. What do you know? You get exactly what we were supposed to get. Okay? Here's another one. So this one's going to be a little more complicated. What I want you to do first is when you're doing synthetic division, that linear factor has to be in the form x minus c. So plus 1 is really minus a -1. Another way of thinking about that is what would that x have to be to make that 0? So I'm going to place -1 here, and then my coefficients, 2, -3, 5, -8. I'm now ready to begin. And again, it's just multiplying and adding. We start by bringing this first coefficient down, then we multiply and add. -1 times 2 is -2. -3 plus -2 is -5. -1 times -5 is 5. 5 plus 5 is 10. -1 times 10 is -10. -8 plus -10 is -18. This last spot here is my remainder. And so I have, and again, I'm decreasing the degree, right? X cubed over x to the first is going to give me quadratic. So 2x squared minus 5x plus 10 minus, and then you could write this as 18 over x plus 1, or remainder -18. Okay? Hey, why don't you guys pause it and do this one? Did you pause it? Did you pause it? I hope you did, so I can say welcome back. I'm going to set this up just like you did when you paused it. Oh, we're missing an X. Missing an X. Wonder if she'll take me back. Horrible joke. We're missing the X to the first, so I'm going to call that 0. Right? Coefficient of 0. And then it's all automated. Bring down, multiply, add, multiply, add, multiply, add. 2 times 1 is 2. Negative 3 plus 2 is negative 1. Add, you get 0. There we go. And so again, we have x to the 4th over x to the 1st. So this is x cubed. This is x squared. And then 10 over x minus 2. All right. So right now, we've got 2 methods for dividing, long division and synthetic division. But why? What are we going to do with it? Okay, there's some important theory that we're going to use these divisions of principle to uncover. So that's where I'm going to go next. And I'm going to largely rely on synthetic division because we're going to be trying to get our hands on linear factors. In other words, factors that can be written as x minus c. All right, so let's go ahead and go back to it. Okay, so now that we know how to divide, let's use it to get some interesting results. In fact, what we really want to do is see if there is a link between factors and roots. And through the following activity, we should get an idea. So what I have here is a chart, and we're going to take and we're going to use each value of c to find p of c, and we're going to divide p of x by x minus c. And I want to see, no joke, no pun intended, if we can make some important observations. So let's do that. What I would like is for you to really do this on your own, okay? And I'll do the first one with you, and then I'd like you to pause the video, go through and do the rest of this on your own so that you can see some important results. Okay, here we go. So the first one, P of C, that's the first thing I want. So I want P, and again, I'm doing that one right there. So C is 3, so P of 3 is going to be 3 squared minus 3 minus 12. So 9 minus 3 minus 12. 6 minus 12 is negative 6. So P of C is negative 6. Next, I'm going to divide by x minus c. And I'm going to use synthetic division for this. So I have 3, and then I have my coefficients. 1, negative 1, and negative 12. Okay? Bring down my 1. 3 times 1 is 3. And I'm adding. Negative 1 plus 3 is 2. 3 times 2 is 6. Negative 12 plus 6 is negative 6. And so what do I get? I get x plus 2 with a remainder of negative 6. All right? Okay. Here, let's try the next one. All right. So I said I would do one with you. Let's go ahead and do 2 of them. Let's do the next one as well. So we want P of negative 2. So negative 2 cubed plus negative 2 squared minus 14 times negative 2 minus 24. So we've got 8 plus 4. I'm sorry, negative 8 plus 4 plus 28 minus 24. So negative 8 plus 4 is negative 4. Plus 28 is 24. Oh, we get 0. All right. And let's see what happens when we divide. Negative 2 And then we've got, let's see, 1, 1, negative 14, and negative 24. All right. Oh, we get 0. And so P of C is 0. And when we divided, we wound up getting x squared minus x minus 12 with a remainder of 0. Interesting. Very interesting. Seems like there's possibly some connection between the remainder and the value of the function. All right. So I want you guys to do the rest. So go ahead, go in there and finish the rest up for me. And I'll when you unpause it, you'll see this list finished. Okay? Pause it and do it. All right, so here's what I've got. So I'm hoping you'll realize, and the observation that you'll make is that these values, the value of the function at C is the same as the remainder when you divide by the linear factor x minus c. This means there's a connection between factors and roots. A root, c is a root if the value of the function is 0, like here and here. Well, x minus c is a factor if the remainder is 0. And since the remainder is the value of the function, dividing by x minus c and getting a remainder of 0 tells me that c itself is a root. Okay, so there's a connection between the roots and the linear factors. That is a big, big result. Okay, so some observations. Well, P of C is the value of the remainder when dividing by x minus c. And so c is a root when the remainder is 0. So this gives us two very powerful theorems that I want to mention. The first one, known as the remainder theorem. If x minus c is a factor of the polynomial p of x, then the value of the remainder is p of c. Let's see how a proof for this might go. So here's what I'm going to do. The division algorithm tells me that I can write p of x as that linear factor x minus c, which would be my divisor, right, times q of x plus a remainder, okay? And the remainder must be lower degree than the divisor. Well, the divisor is linear, so that remainder must be degree 0, which means it's a constant. R is a constant. Okay, now watch this. P of C equals C minus C, Q of C plus R. Well, that's 0 times q of c. Again, I have no idea what q is, just some quotient, which tells me that p of c equals the remainder r. Okay, there we go. The division algorithm is the key. Rewriting the function, or the polynomial, more specifically, in this form, and then showing that when you plug in c, all you're left with is that constant remainder. All right? Okay, well, c is a 0. This is the factor theorem of the polynomial if and only if x minus c is a factor of p of x. All right. Well, let's play around with this. So this proof, there's a logic lesson here, if and only if. So what we're going to do is we're going to take turns with the hypothesis and conclusion and then swap them. So this is a logical note here. I'm going to go this direction, meaning I'm going to say, suppose C is a 0 of p of x, okay? Well, again, by the division algorithm, I can write p of x as x minus c q of x plus the remainder, right? That remainder r. Well, p of c equals 0 is going to tell me that r equals 0, right? And that's really from that last theorem. Okay, it's the value of the remainder. If you plug c into this, you get r. Okay. Now let's go the other direction. So what do I mean by that? Now I'm going to say, suppose x minus c is a factor of p of x. Well, then the remainder is 0, right? So I can write p of x equals x minus c times q of x. Well, I want to show that c is a root. Because I have a factor, that lets me get rid of this remainder out here, which means when I plug in c, I get 0 times q, which is just 0. In other words, c is a root. Okay? And that proves the theorem. Again, the logic here is we're saying, suppose c is a 0, show the remainder is 0, and then go the other way. Suppose x minus c is a factor, let's show that c is a root. Okay? I mean, after all, a remainder of 0, right? I guess I should add this just to be thorough. That tells me that x minus c is a factor. Okay? So there we go. All right. Again, I'd like you to pause it and work these out yourself. And when you come back, you'll see my solutions. So pause it. Pause it. I would like to welcome you back after you have paused it. Let's take a look here. Number 1, find a polynomial with roots 2, -3, and 1 with leading coefficient 2. Well, let's think about this. If the roots are 2, -3, and 1, that means it can be factored as x minus 2, x plus 3, and x minus 1. But here's the other thing. I want the leading coefficient to be 2. Well, right now, the leading coefficient is 1, right? If I multiplied this out, Well, I can fix that. 2 right there. Okay. And if you don't believe me, well, let's see what happens. I'm going to do this. I'm going to multiply this out. 3x minus x is 2x. 3. Keep going here. We've got x cubed. And then let's see, for my x squareds, I've got a negative 2x squared plus 2x squared, so no x squareds. My x's, I've got a negative 4x and a negative 3x, so negative 7x, and then plus 6, and then distribute that too. Sure enough, my leading coefficient is 2. Okay. How about number 2 here? Factor the polynomial completely. Well, let's see. X to the 4th minus 166x squared plus 1600. Well, what I'm going to notice is that this thing sure does look quadratic in x squared. Right, x to the 4th is x squared squared. So can I figure out what could go in these in spots, those constants, that would give me that polynomial? Let's try to see what we find. Sorry, guys, you know what? That needed to be a 116. Real-time editing here. All right, so that should be 116x squared. So we have x squared minus 16 and x squared minus 100. And now we can keep factoring. X squared minus 16 is x plus 4 times x minus 4. And x squared minus 100 is x plus 10 times x minus 10. Okay? And now number 3. So roots 2 and 3 of multiplicity 1 and a root of negative 1 with multiplicity 2. Okay. 2 and 3 of multiplicity 1. So that's going to mean x minus 2 is a factor, x minus 3 is a factor. A root of negative 1, so x plus 1 with multiplicity 2. Okay. And there it is. And again, notice, you tell me the roots, I know the factors. Okay. It's a big connection in this section. All right, guys, so we had some wonderful results in this section. The factor theorem, the remainder theorem, being able to tell from synthetic division what the remainder, what the factors are. And if you have a factor, you also know a root. If you have a root, you know a factor, a linear factor, okay? Big results as we move towards being able to fully factor a polynomial under the right conditions. All right, so get some work done, get some problems solved, go back and rework what you saw me do here in lecture. And as always, I wish you the happiest of studies.